and we'll be watching some pendulum swing, and especially timing the time for the periods and seeing as we adjust various features of the pendulums, how does that affect the period, or does it affect the period, and then maybe we can see if it does it in the way that we expect according to our analysis, and maybe see a couple other things about pendulums as well, maybe a little bit about springs. Let me see. The first thing I want to say before I go too much further is there's a typo in the homework listed for this week. So let's just look at that. 1201 spring 2020. Make sure I'm looking at the right course here. Right here, this is the week we're on, 20th to the 24th. Most of the questions are from chapter 14, but there's 2 questions here from chapter 13. Fairly involved questions, a little bit longer to work out the work on those for orbits and gravity. But it says to do chapter 1328 and to do chapter 1375, and there is no chapter 1375. Flipping back to chapter 13 here. Chapter 13 ends at question 70. That I don't know how it came into be 75. It was supposed to be question 50. So it's 28, which is correct. And then number 50. What's 28? I'm just trying to remember. Okay, yeah. 28 and 50. So number 50 is about 2 planets of mass little m, same mass little m, orbiting a star of mass capital M. The planets are in the same orbit with the same radius, so a lot of information there. And the question is to find a formula for the orbital period t. The goal of number 50 is not a number, a numerical calculation. It's to come up with an equation, capital T equals. I think it's implied, since it gives you a radius in the question, since you're only supposed to really have in your answer the other quantities that appear in the question, which is capital M, mass of planet, there's mass of star, excuse me, lowercase m, mass of both planets, lowercase r, radius. Probably just those 3 pieces of information, and then capital G, Newton's constant capital G will definitely play a role as well. The other thing I was just going to mention is, if you were to glance, this is not assigned, so it's only number 50. That's the only change in the assignment. But if you were to look at number 68, which is one of the last questions in chapter 13, chapter 13, 68, you'll see something pretty similar to what we talked about, I think, last week, about trying to use an elliptical orbit to link a small circular orbit out to a larger circular orbit. They have a diagram very similar to the one we made, and some of the algebra worked out, which I think is similar to what I would have told you some results for. Okay, so there's that. Chapter 14, lots of questions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 from chapter 14, and then 2 from 13. So a little bit bigger assignment. Some of the chapter 14 questions, a decent number of the chapter 14 questions is to kind of work out the proper cosine equation or sine equation, often cosine, to describe simple harmonic motion if we're given a couple clues. In general, you'd need to be told 2 clues, something that would help us pin down amplitude and something that would help us pin down period. Sometimes you're given a 3rd clue, a 3rd data point about the sine wave, about the simple harmonic motion, and that would help us pin down something called the phase shift or the phase constant, which we'll talk a little bit about today. But mainly what I want to talk about today is energy in simple harmonic motion, and then look at a vertical spring briefly and a pendulum. The lab is due tomorrow. It's the lab from last week. What's last week's lab again? Oh yeah, the balance tables. That's right, the balance tables. That'll be due tomorrow, yes, and I'll put up the submission spot on Moodle as an assignment. That is correct. And let's see, what do you have to submit from that? I'm trying to remind myself. I gave you a bunch of masses, so it's to basically fill out that Excel table by filling in torques and summing up and getting total torques, right? I think that's basically what you're asked to fill in, and it's all you'll need to submit is the Excel file kind of one table for each of 6 arrangements from last Thursday. And depending on which lab group you're in, you have different data to use for that. Let's see. Yeah, so I think that is pretty good for homework. If you looked at the schedule, maybe I should do one more thing. If you look at the schedule for today, we're just about on target. It says problems, which kind of is my way of saying a buffer day before a new topic's going to begin. Really, what that probably should say, I don't exactly know why I said problems. It should probably say section 14.6, because section 14.6 is titled The Pendulum. And that's probably what I should have called it. There's only one question from section 14.7 about damped oscillations. I can't remember which question that is. I think that's number 71. So that I think is a little trickier one, number 71, but it's the only question from section 14.7. We're doing sections 14.1 through 6 pretty fully. I know it's not listing 5 and 6 there in the reading column. What's section 5 called? Vertical oscillations. Yeah, we're definitely doing 14.5 and 6. Really, I should have said, I really should have said 14.5 dash 14.6. That's probably what I should have said. I don't quite know why I didn't say that. So 2 things there. Okay. Great. Just looking at who's with us. Okay. Okay. So gonna start talking about vertical springs. Vertical spring. There's a Desmos sheet that I'm going to bring up, and then kind of one print off from the Desmos sheet has been put up on Moodle. I'm going to talk about a vertical spring. What are the key thoughts to carry over from Monday? If there is a linear restoring force, you got simple harmonic motion. If there is a parabolic, kind of quadratic, parabolic shaped potential energy function, you've got simple harmonic motion. If the motion of the object as a function of time is sinusoidal, perhaps described by a cosine, you have simple harmonic motion. And if your period is independent of the amplitude, in particular, the equation T equals 2 pi squared of m over k as a specific equation. But if period is independent of the amplitude of the oscillations, you've got simple harmonic motion. And if one of those 4 is true, they're all true. So nope. So let's draw a free body diagram for a vertical spring, and let's think about the forces that are acting on a vertical spring. So I'm going to try to use the linear restoring force as a way in to figuring out, is a vertical spring simple harmonic motion exactly? Is it almost simple harmonic motion? And we'll also touch on potential energy. So I think I'll zoom back just a bit. Go. Let me do that. Okay. All right. So what would the free body diagram be for a vertical spring? Yeah, it's too far back. Okay. What would the free body diagram be for a vertical spring? I'll do it over here. Oh, my board's wobbling. That's why. Okay. So I'm going to draw kind of 2 pictures here. This would be the spring with nothing attached to it. And then now we're going to have the spring, and I'm going to attach something to it. This is spring constant K, this is same spring, and this is going to be mass M. Okay. And then I'm going to kind of do this for reference. So this is, we use the term equilibrium when talking about oscillations. Equilibrium is the point where the force is 0. That's what equilibrium pretty much always means in physics and engineering, is like net force equals 0. So You might kind of compare this point here. I'm going to talk about this point as, if I talk about a position, I'm going to take it to be that point right at the end of the spring. If there's nothing on the spring, it would rest, let's say, at a high location. Then you put some mass on the spring, and now it's going to rest somewhere else. So now we need to be a little bit careful. Like if we say equilibrium, we might want to be a little careful. Do you mean like the old equilibrium in black? Or do you mean like the new equilibrium? Let's say the new equilibrium is kind of right here. And I'm not going to draw the object at the new equilibrium. I just want to kind of show it. So this is the new equilibrium. What do you think I mean when I say the new equilibrium? If this object were, let's say you attach the block and you pull the block down to right here, and then you let the block go. It's going to oscillate, but let's say you just let it oscillate for an hour. What's going to happen if you set this oscillating and come back after lunch? It's going to be at rest somewhere. And I'm saying by marking the blue location, I'm saying basically this object's going to come to rest right here.
And take notes.
It's not going to come to rest at the, the old equilibrium. So I'm going to call this one the old equilibrium. Okay. And then let's draw a free body diagram. How many forces is this block feeling? Let's say no air resistance, nothing like that. How many forces is this block feeling? Gravity's pulling it down, mg. I'll just draw it off to the side, I think. Force of gravity is mg. And then if you're below the black point, the black spring pulls up on you. If you're above the black old equilibrium, the black spring pushes down on you. So the forces here are basically spring force up. Spring force is always going to point back at the black dotted line, and gravity down. And right now, which one is winning? If I draw the blue equilibrium here, but I draw the object below it, which of these forces is going to be stronger, or are they going to be equal? We're going to figure out that if you're below the blue spot, the red force upward is winning, and it's going to pull the mass back up. But if you're above the blue spot, gravity down is winning, and it's going to pull the mass back down. And the only place where the objects could come to rest is where those two forces are equal, and those two forces are going to be equal right at the new equilibrium. Old equilibrium means spring force is 0. New equilibrium means spring force equals gravitational force. But there's one important thing I want to say here about the gravitational force. The gravitational force doesn't change strength, right? The mass is the same, m times g is the same no matter where it is. So this force varies, but this force is constant. And right now, I'm going to say in my picture, I'm going to draw it where I'm below equilibrium, and right now, the acceleration would be upward. Because the spring force is going to win, maybe I should draw the spring force longer in the sketch. Okay. What's the formula for spring force? Negative kx, negative ky. I think I'm going to call this direction the y direction. I'm going to call y equals 0 right here. And then y, not surprisingly, is going to kind of increase as you go upward. So we're going to make a new choice in a little bit, and we're going to switch and probably start to measure y from the blue location. But for right now, I'm going to measure y from the old equilibrium, where the spring would be if nothing were attached to it. In this case, gravity is a negative force. Spring force is opposite to y. So this is what I would write down for an equation based on F net equals ma. Upward acceleration equals spring force plus gravitational force. I'm going to write the equation over here. ma, and I add the forces. And then let's think about directions. I'm going to say up is positive, so I'm going to say A is positive. I'm going to say up is positive, so I'm going to say minus force of gravity. And then what we typically do with a spring is we typically do negative ky. So if you kind of plug in our facts here, we get negative mg ma is negative ky minus mg. And right now I'm at a negative y position. So you want to think about the signs a little bit. I've drawn the picture at a negative y position, and since y is negative for the sketch, negative ky is actually going to be a positive contribution to the force for the position that I've kind of drawn. But this is kind of what I would say would be a good equation here. We always want y to be positive upward. Okay. Yep, we always want y to be positive upward. There's a negative sign in the Hooke's law for a spring, and gravity is going to be downward. So do we have a linear restoring force or not? This is the net force. Is that a linear relationship? Yes, it is. The problem is it's a linear relationship that doesn't go through the origin, which basically is saying the object's equilibrium position is not going to be the black. What is the blue going to be? What is this distance? How far below the unweighted spring will the weighted spring hang? And it's not very hard to work out. Just set the net force equal to 0. Set the net force or the acceleration equal to 0 and solve for y. What do you get if you set the net force equal to 0 and solve for y? I'm going to maybe use this spot of the board to do that. New equilibrium set A equals 0, solve for position. So I set A equals 0, I add ky to the other side, and I get ky equals negative mg. I think I'm going to call this y0. And then, so this is y0. So, and then I'll just divide by k. Okay, what is this telling us? The new equilibrium is below the old equilibrium because it came out negative. M is positive, G is positive, and K is positive, right? So the new balance point will be some distance below the old balance point, and you can calculate it by doing mass times gravity over K. Really easy. Force of gravity is mg, and force of a spring divided by K is position of a spring. Okay, and now I'm going to kind of take this equation and I'm going to shift my thinking to center on y0. So, you know, this is y0. Y0 is negative, meaning below, because gravity didn't pull the block, didn't pull the spring up, it pulled the spring down. But if you were to take this formula, then you could rewrite it in a little bit different way that might be a little bit preferable. And I'm just going to do that quickly. I'm just going to kind of, whenever I see mg, I'm going to write it in terms of y0. So this is true, but what could I substitute in place of mg? If I solve this equation for mg, then this would be mg is negative, is that right? Okay, there was a negative. Negative mg, and then I'm going to say for mg, I'm just going to solve this, it's negative ky0. And minus a minus, I'm going to write this out, and I'm just going to kind of factor a negative k to the front, and we could write the formula for a vertical spring like this. Negative ky minus y0. Keeping in mind that y0 is actually going to be a negative value, I think this is correct. What kind of equation is negative ky minus y0? Y0 is this value. It's a constant. K is a constant. This is a straight line. if you think of y as the independent variable, this is a straight line with slope negative k, but it doesn't go through the origin. It goes through a point shifted from the origin a little bit, which is basically saying we still have simple harmonic motion here, but don't think the equilibrium is going to be up here. The equilibrium is going to be kind of suppressed downward due to gravity. And all that gravity really does to the vertical spring is it recenters our eyesight from here to here. And other than that, it doesn't affect the motion of the spring at all. So all the equations for a horizontal spring, especially equations involving period or angular velocity or frequency, they still work just as well for a horizontal spring. The only difference is you have to shift to the new equilibrium. And then you should really measure everything from here. What is y minus y naught? It's basically measuring from blue instead of measuring from black. So does gravity change how long it takes a spring to bounce? No, it doesn't. Does gravity change anything about the bounces? One issue. It changes where the middle of the bounces are. Instead of the middle of the bounces being up here, gravity says, well, the middle of the bounce is going to be down here. And then you're doing the same type of motion, taking just as long down here that you would have been doing somewhere else if there'd been no gravity. If you turn off gravity, what happens to y naught? G becomes 0, so y naught becomes 0, and you get ma as negative ky, which is, of course, directly Hooke's law. So basically, a vertical spring is simple harmonic motion, and you don't have to change the period fact at all. It is still period equals 2 pi squared of mass over k. M and k are always the two really key things, and they very often end up as a ratio. Here's m over k as a ratio, right? What happens if you kind of, solve for acceleration? You'll get k over m. It's almost always the ratio k over m or the reciprocal m over k that really matters when you're talking about simple harmonic motion. How strong is the spring? That's k. How heavy is or big is the object? That's m. Stronger springs make things oscillate rapidly. Higher masses, bigger objects are harder to move quickly, harder to change their motion quickly, so they take longer to oscillate. All right, what about potential energy? What about potential energy? It's really easy to do potential energy because most of the tricky stuff here, if you're going to make a mistake here, it probably has to do with the positive signs and the minus signs, because force and acceleration are vectors and you need to think about the directions. But for potential energy, it's not a vector, it's just a scalar, so you just add it. So what's the formula for potential energy of a spring? 1/2 ky squared. I'm going to say x, in this case I'm going to call it y because it's vertical. What's the potential energy due to gravity? Positive mgy, right? So what is the potential energy for a vertical spring? You just add those together. And at this point, I think I'm going to go to the share the screen and show you some, well, let's try to get that out of there. And show you Desmos worksheet. That's it right there. Okay. What is this formula right here? I didn't label the axes. Why did I not label the axes? X-axis position in meters, and y-axis is potential energy in joules. And I like having the arrows. And I only want those arrows. Okay. Let me save that one. Okay. So this is the potential energy right now. It's just what's the formula in purple? 1/2 kx squared. That's the potential energy of just a spring. You might say either a horizontal spring or a vertical spring, but there's no gravity. And that is what we love to see, and that means simple harmonic motion, as long as that is a parabola, and it looks to be a parabola that's increasing the way it's supposed to be increasing. So let's zoom back in here. What are the numbers that I'm using? There's some sliders over here, and I'm going to kind of, give you guys this link here. Maybe I'll just quickly, actually, that's not the way to do it. This is the way to do it, better way to do it. Copy that. And I'll just pop this into the share quickly. So desmos.com/calculator/VQNOER9IAI. You guys can try that one out and do what I'm doing. What are the values I'm going to go with? Right now my mass is 0.05, which actually isn't affecting this graph because purple only depends on K. Other graphs will depend on M and K. G, 9.8. K, 25 newtons per meter. And eventually there'll maybe be a couple other things, an E slider for energy and a B slider, which isn't quite so important. I probably should have used a letter other than B. Okay, so that's simple harmonic motion for sure. Now, what's the actual potential energy function for a vertical spring? Keep in mind, whenever you see X over here, it's basically a Y coordinate. X on the Desmos screen is what Y is here. It's Y measured upward from right here, from the old equilibrium. Okay, so what is the actual potential energy of the new vertical spring? That is the potential energy of the new vertical spring. Okay, now let's apply our tests. In order to have simple harmonic motion, if you're looking at potential energy, you want to know, is it parabolic? If there's a parabolic potential energy about some minimum point, it's simple harmonic motion. So is the red curve parabolic? Yes, it is. Is it the same parabola as the purple curve? Well, actually, they're the same shape, just the red has been shifted a bit from the other one. So what is the overall effect of adding mgx to go from purple, no gravity, to red with gravity? It doesn't change the overall shape of parabolic. It doesn't even change how steep the parabola is. So you will get simple harmonic motion in the red curve back and forth about the low point of the red. Very, very similar, basically identical to the simple harmonic motion you would get in the purple curve back and forth around the bottom of the purple curve. What's the only difference between the purple and the red? The purple is going to oscillate around 0, but the red's going to oscillate. In this case, it looks like it's going to oscillate around the low point. It's going to oscillate around negative 0.0196 as a y coordinate. And then this energy we'll get into later. How do we calculate that point right there? I think that's that point right there. Yep. There we go. How do you calculate that point? Well, that's what this is. That's negative mg over k. So what is the new equilibrium position? It is 1.96 centimeters below the old equilibrium position. And that's based on having mass be mass be 0.05 kilograms, which is 50 grams, and a spring constant of 25 newtons per meter. And G is G. Okay. What happens to this graph if you attach a bigger and bigger mass? You're just going to have simple harmonic motion. The purple and the red are the same shape, but now you're going to get simple harmonic motion. And if you guys can see that number, 0.0, let me make that smaller. It's taking up too much of my screen. There we go. Now it's simple. Now if you attach a 110 gram mass, it's still simple harmonic motion for the spring, but now the equilibrium point is 4 centimeters below the old equilibrium point. Where is that? So what was the effect of gravity? The effect of gravity was to kind of shift our view, and instead of centering on 0, 0, now we're centering on this point. What does this number represent? That is the energy to sit right here, 3 or so centimeters below the old spot. Is the energy 0 to be right there? No. The energy is negative. The least important number on here is the negative 0.012293. Why, if you're oscillating back and forth inside this red bowl, which is kind of how you want to think about it, why is this number not very important? Why is 0.012293 not very important? Because all that matters about energies are changes in energy. So if all your energies are shifted down 0.019, that's not really going to change the behavior of the system. What would change the behavior of the system is if you change the shape of the red curve, not if you took the whole red curve and moved it down. And that basically is kind of the idea of when you do an integral, you get an undetermined constant like a plus c. So if you want plus c to be negative 0.01, great. If you want plus c to be a different value, fine. You still have the same basic force and potential energy relationship. So I'm just going to write all that matters about energy is, all that matters about energies are highlight changes. That's not how you spell changes. Changes in energy differences. So I'm now going to use the fact that an energy constant doesn't really mean much in physics. And I'm basically going to kind of like just recenter my energy scale down to here. And basically what you're pretty much doing is, if you take the red equation, if you complete the square for the red equation, you will get something that describes the red curve. And then gravity has just been subsumed. The mg's just show up in two ways. It just shows up in shifting your vertex over negative, meaning downward for position, and down, meaning lower energy. What were some of these guys here? I'm trying to remember what the other sliders are. Okay, let's say this is what I meant. Let's say you have this much energy. A lot of times we represent energy by a horizontal line. I'm going to go back to the purple. Let's say, let's say your energy is, what energy did I come up with? 0.04. 0.004, excuse me. If you have a horizontal spring or you have a spring with no gravity, the object will move back and forth, and where will it turn around? It'll turn around 0.0179 centimeters above equilibrium, and it'll turn around at negative 0.019 centimeters below equilibrium. Get that to highlight. Okay. So how could we calculate those? Very easy. What's the potential energy function? 1/2 kx squared, and we know k is somewhere on here 25, and then just set it equal to the energy. Where the potential energy curve crosses the horizontal energy line are the turnaround points. Can you ever get, could this object with this much energy, could it ever get to 0.03? No, because at 0.03, well, let's say, could it ever get to 0.02, trying to get to 0.02596? No, because that requires more energy than the blue line says it has. So the allowed region is when the potential energy curve is below blue. You can't get to the region where the potential energy curve is above blue. Now, what if instead of giving 0.004, 0.004 units of energy, what if instead of giving it to the horizontal spring, you gave it to the vertical spring? Now, this object isn't going to oscillate about 0. It's going to oscillate about where we said before. Oh, not that one. I meant this one. And how far to the left and the right is it going to go? It's going to oscillate a very long ways. It's going to oscillate from 0.0047 above the black dotted line to negative 0.6746, which is obviously below because it's negative, the black dotted line. And it's going to speed up a lot, slow down to 0. Speed up a lot, slow down to 0. So a couple thoughts are, when potential energy is low, kinetic energy is high, and you're moving fast, highest speed is when you move through the bottom of the potential energy curve, which we call equilibrium. In either direction, you'll hit your highest speed at the adjusted negative mg over k spot. And what's your speed right here, and what's your speed right here? Well, if you go to right here, energy is kinetic plus potential, and right here, energy equals potential energy. So you have 0 kinetic energy, and you stop moving with 0 speed and you turn around. No, that's what I'm trying to get. Okay. And that takes me to a little printout, which I also handed out or made available. Let's see this one. So this is the same sheet. Actually, I'm going to go back to the other one. I'm going to adjust the numbers to match this exactly. This was a mass of 0.1 kilograms, 9.825, and I made the energy negative 0.005. So I'm going to go to the other sheet and just mash these numbers up very quickly. So mass is 0.1 kilograms and E is negative 0.005 joules. Okay. I used to have a mass of 0.8, which is 80 kilograms, or sorry, 80 grams. And now I'm going to make it 100 grams or 0.1. And I'm going to change the energy to be negative 0.05. Okay. And I think now this should be pretty much exactly the same as this graph here. Okay. So let's just look around and think about how to interpret this. Mechanical energy, or energy in blue, is potential, which is red, plus kinetic, which is green. So the potential energy is negative, the kinetic energy is positive, and together at this location they add up to be E. What would the red and the green look like if you went to kind of closer to like where my cursor is right now? Less negative potential energy, which is more energy, but a short negative line and a small positive green line. What if you get right here? Kinetic becomes 0, and it means you're turning around. Turnaround points are when total energy equals potential energy, which leaves you with no kinetic energy, which means your speed is 0. And then we picked a couple points out here. I highlighted one point to the left of the equilibrium just kind of for reference. Potential energy curve, total energy line, tangent line. What does this tangent line represent? This is a potential energy in U versus a position, you could call it X or Y in measured in meters. What does the slope of potential energy represent? Slope of potential energy is, what's the units of the slope? What are the units of the slope of potential energy? I'm typing that in the chat. What are the units of the slope of PE versus position? Question mark. Well, what's the units of potential energy? What's the units of position? And when you make a slope, what are you doing with the units? It's like change in Y, which would be a change in potential energy, divided by a change in X, which is position. So the units of the slope equals energy units over position. Energy units over position units. And what does that come out to be? Units of slope, I should have said. And that ends up being joules over meters. Can somebody tell me what a joule over a meter is? Let's see, what's a joule? Maybe we'll use kinetic energy, 1/2 mv squared. So a joule is kilogram times meter squared over second squared. And then what happens, what do you get if you divide that by meters? You get a Newton. You get kilogram, somebody wrote Newton, that's definitely correct. You get kilogram times meter over second squared, and that's a Newton. So what does the slope on the graph represent? What's measured in newtons? Force is measured in newtons. So on this graph, the one extra thing that I've shown here on the handout, which I haven't highlighted yet, but it's just further down in the Desmos sheet, is I've drawn in a tangent line. I picked a particular point, I guess negative 0.06 meters. And that's the tangent line. What is the slope of this tangent line? I think that's maybe written right here. KB plus mg is the slope. What's KB plus mg? Negative 0.52 joules over meters, but joules over meters is newtons. Let's go to the graph. There's one other tweak. Is the slope of the graph directly force? Very, very close. Can anyone tell me what's the difference between the slope and force? To go from potential energy to force, you have to take a derivative, which is like a slope of a tangent line. You have to do one other little thing. If you're at 6 centimeters and the equilibrium is only at 4 centimeters, you're below, the black dot is below equilibrium, right? It's at a lower position on the graph. Which way is the force if you're below equilibrium? Upward. And yet the slope came out to have clearly a negative slope, and the slope as a number is negative 0.52. So what is the other thing you have to do to the slope to get actually the force? The force is the negative of the slope. So what is the slope in this part of the red curve? Some negative value. And that means in this part of the curve, the force is in the positive upward direction. What's the slope right here at the bottom of the curve? 0. Force is 0. And if you're above equilibrium, the slope is positive. But if the slope is positive, that means the force is negative, meaning when you're above equilibrium, the force points downward, not upward. So really, I should say force is the negative slope. Force equals negative slope of PE versus X, or you could say Y. What's the mathematical way to say that? Negative derivative so if you take the derivative, you should get back to some of the stuff that was written here previously about force. Statement 1, here's statement number 1. Change in potential energy is the negative integral of the force. And I'm just going to do it in one dimension, so I don't have to do a dot product. What's the other way to say it? This is always, 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 always how potential energy and force relate. Integrate the force, pop a minus sign, you got the PE. And when you integrate, you get an undetermined constant that you can adjust however you want. Going the other way, take the derivative of the potential energy, pop a minus sign, and you have the force. So you can just kind of look around on there a little bit. I think I'm going to go to it one more time. I'm going to go add this dotted line stuff. So if you want, you can kind of just see how to do that. Okay, so I picked a dot. That's the dot. Sorry, I picked a dot. And then I can move the dot around. Whoop, moving a little too fast. And then I can draw the tangent line. And what is the interpretation of this negative 0.77 number? Well, let me do two things. What's the interpretation of this number here? That's the energy in joules. Well, what's the interpretation of the slope? If you change the sign of the slope, then you get the force. So at this location, the object has negative 0.00735 joules of energy, which it's allowed to have because it has to be below the blue, and the blue is negative 0.005. So it's below the blue with this much energy. And right now, is it going to sit there or is it going to move in one direction or the other? It's going to move towards the lower potential energy. So it's going to feel a rightward force towards lower portions of the red curve, and the strength of the force will be 0.77 newtons. What will the acceleration be? Take force and divide by mass, you'll get acceleration, et cetera, et cetera. And then what if we just move this around? I need to be careful not to go very fast. When you get close to equilibrium, what happens to the force? Dies out towards 0. What if you get right to equilibrium? I can't quite get there. You know, it's negative point, whatever the number is. Can't quite get there. Negative 0.392, but I can get close. You know, I could type it in there. Maybe I can. I don't want to lose the slider. Oh, I didn't. Okay, so now what's the force? 0. On the other side of equilibrium, life's very similar right of equilibrium as left. It's just everything's flipped in direction. It's just as steep here, though, as it was, you know, like kind of over here. Let's pick a spot. I'm going to pick a spot right here. I'm going to write these numbers up on the board and do a calculation, and we're going to get back some of the numbers that are maybe in this worksheet. Okay, I'm going to write up K, I'm going to write up M, and I'm going to write up K and M are the main ones. And then I'm going to pick this location, and I want to work out a couple things. I'm also going to give you an energy, but before giving you the energy, I'm going to do a couple calculations about force. What is the force of the object if it's got a mass of 0.1 kilograms and it's got a spring constant K value of 25 newtons per meter, and you are at negative 0.02? Okay, erasing all this. All right. For safekeeping, M 0.10 kilograms, K 25 newtons per meter. Okay. And then I'm going to choose a location, and my location on the worksheet is called B, but on here it's going to be negative 0.02 meters. So that's like 2 centimeters. What's the force? What's the acceleration? I already had the equation for force up before I erased it. I'm just going to put it back. The formula is negative Ky minus mg. This is negative because it's downward, and this is negative because the force is opposite to the y value. When y is negative, spring force is positive, and vice versa. So let's just plug all this in. The force of the spring is negative 25 times 0.02. And then the force of gravity is 0.10 kilograms times 9.80 meters per second squared. Oops, I missed a minus sign. That's pretty important. So the spring force comes out positive, gravitational force, of course, negative. I can do most of that in my head. I think I should be able to. So the spring force is positive 0.5 newtons. And then the gravitational force is negative 0.98 newtons, right? And what's the net force come out to be? Negative 0.48 newtons. Okay, if I take that and I divide by mass, I'm going to get an acceleration. So I think I'll just convert that to an acceleration. And the mass is 1/10 per kilogram. So the acceleration is going to be negative 4.8. Okay. Does that indicate we're above equilibrium or below equilibrium? We're going to feel a downward force and acceleration, so equilibrium must be somewhere below us. The net force and the acceleration always point at equilibrium. Always point like back to the balance point. What is the equilibrium position? That's my next calculation. It's on the file many times. What's the equilibrium position? set the force equal to 0. That's what equilibrium means. We already did that. Solve and get y naught. In the previous notes on the board, I called it y naught. So what is y naught? It's mg. It's negative mg divided by k. So I'm not going to write that up here. I'm just going to write the value. What is the equilibrium position in this case? Negative mg, well, we know that that's negative 0.98 divided by spring constant. So negative 0.98 newtons divided by the spring constant. And that'll come out to be position in meters. The equilibrium position is negative 0.392. My board bouncing all over the place. Okay. And sure enough, we're not at equilibrium. Here's another quick way to calculate the net force. I'm going to do it a second time and get the same number. How far away from equilibrium am I? Instead of using the 0.02 meters, which is what I did in the black calculation, what if I just said, how far from equilibrium am I? And it turns out that I'm above equilibrium, right? This minus that. Negative 0.02 minus negative 0.0392. This is 0.0192 meters above equilibrium. So measured from the black dotted line, I call it negative 0.02. Measured from the blue dotted line, this is the blue dotted line. Measured from the blue dotted line, this is positive 0.196 meters. And then how do you get the force if you measure from the new equilibrium? Only do negative ky. If you measure from the new equilibrium, you don't have to do any gravity calculations, which is kind of nice. So just find the distance from the new equilibrium and multiply by negative k. And I'm multiplying by, negative times 25, negative 25 times 0.0196. And I'm getting negative 0.49. Oh, I typed in the wrong decimal. Negative 25 times 0. This is supposed to be a 2. I don't know where I got a 6 from. There's a 2 there, and I wrote a 6 there. Okay. Distance from new equilibrium times the negative k. And I got negative 0.48, which is the same. Now, what if somebody asked you, how fast is the object going when it gets to this point? So what if they didn't ask you, what's the acceleration? What if they ask you how fast it's going? That takes a little more information for us to calculate because we don't know how big the bounces are. Somebody has to give us information about the size of the bounces. And the way to do that, a very common way to do that, would be to either be told the turnaround points. So you could either tell me it started at 00549 and we let it go and it sped up to the left, slowed down, turned around at this point. But I think an easier way to do that is basically we're talking about the blue line, right? What's the energy value? Negative 0.005 joules. Is it okay that it's a negative energy? Yes, it is okay that it's a negative energy. What's important is that the potential energy is below the blue line. If the blue line happens to be negative, that might not be a deal breaker. What's a deal breaker is the red can't be above the blue. So if the blue is at negative 0.005, I only care about the red portion of the curve where the potential energy is less than the total energy. So new calculation, if the total energy is negative 0.005 joules, how fast will the object be going when it gets right there? How do I do that? The best way to find a speed is to not use a force approach. The best way to find a speed is to use an energy approach. And again, I'm going to do this, I think, twice. Once measured from the old equilibrium to get the final speed, and once measured from the new equilibrium to get the final speed. So here we go. Energy is U plus K. energy is potential plus kinetic. I'm going to measure from the old equilibrium. What's my potential energy function? 1/2 ky squared plus mgy. And then I add on, k, which is 1/2 mv squared. Okay, and you told me that this was negative 0.005 joules. So I plug it in there, and let's just calculate this much, and then subtract them, move them to the other side of the equation. What's the y value? Here it is. K, here it is. M, here it is. And this is what's visually shown in the Desmos. 1/2 times 25 times this negative number squared. When I'm squaring it, it doesn't matter that it's negative, but it's going to matter that it's negative when doing mgy. Yes, I happen to get this number. A little bit of coincidence, but I ended up getting 0.005 joules. And I'm going to add on mgy. And mgy is 1/10 of a kilogram times 9.80 times negative 0.02. And this is negative 0.0196, not joules. So if I move these two terms to the other side, how much kinetic energy do I have left? Maybe I'll add them up and mention what that number is. The total potential energy is 0.0146, which sure enough is below the energy. The total potential energy needs to be below the energy, otherwise it represents a non-physical situation. I'm going to move this to the other side, and what do I get for kinetic energy? I get that the kinetic energy is whatever you have to add on to this to get this. I get that the kinetic energy turns out to be positive. Kinetic energy can't be negative. 0.096. Total energy can be negative. Potential energy of gravity can be negative. Total potential energy can be negative. But potential energy of a spring has to be positive, and kinetic energy has to be positive. And then I just solve for velocity. I double that, I divide by mass, and I get a velocity. What's the last step? What's the last step mathematically in solving for V? You got to take a square root, right? And when you take a square root, what should you technically probably do? You should do plus or minus. And that actually is pretty physically meaningful here. So when you get to this position, what is your velocity? Well, I can tell you it's either plus or minus 0.438 meters per second. So the result here was, at this position, the velocity is either plus or minus 0.438 meters per second. And at this position, the acceleration is negative 4.8 meters per second squared. Okay. Why is this plus or minus? Like, what does that mean about the object? A mass on a spring. How fast are you going when you get to right here? If you're following a cosine wave or a sine wave, every time you cross a certain height once on the way down, and then you cross it later in the oscillation on the way up, right? The speed is known, but the direction is not known because we don't know which point in the oscillation you're at if all you tell me is I'm 2 centimeters below the old equilibrium. I said I was going to do this a second time. I don't think I'm going to do it a second time, but how would you do it the second time? Measure from the new equilibrium, which ended up being positive 0.192 meters. And if you measure from the new equilibrium, what can I erase if I'm going to measure from the new equilibrium? I don't need to do gravity calculations. I still need to do 1/2 ky squared, but gravity has been totally accounted for by shifting from negative 0.002 meters if I shift that to the positive 0.192 meters. Maybe I'll call it like y prime. Y from the blue spot was positive 0.0192 meters. And guess what you're going to get if you do 1/2 k times this number squared? You're going to get the same results. It's going to end up mimicking the calculations done up here. Okay. So this is something you need to get kind of comfortable with. Can you go back and forth between position, force, velocity, acceleration for simple harmonic motion? I'd say they kind of come in a couple groups. I'm going to write the groups over here. Position, force, acceleration. Those are all force concepts. And you can use things like F equals negative kx, capital F. Trying to write something here. So if you had force, position, acceleration, I would use things like ma is force and force is negative kx. If you measure from the new equilibrium, you don't have to include negative mg. If you measure from the old equilibrium, you need to include negative mg. What if instead you're talking about things like position, energy, speed? Those are all energy concepts. And the energy concepts would probably be total energy equals 1/2 mv squared plus 1/2 kx squared. And what is most important to know about the total energy? It is constant. And that's indicated on the graph by it being a level line, right? Okay. One last thing I'm going to say. What do you do with all these equations which apply to springs? What do you do to all the spring equations to make them pendulum equations? If you do one little replacement, all the spring equations can be now thought of as pendulum equations. And here is the small replacement. It's written pretty well in the chapter summary. And I just wanted to see the way they wrote it. Here's for pendula. For a pendulum, replace K with mg over L. Anywhere in any spring formula, if you see the if you see the K, if you replace with mg over L, it will now be a pendulum equation. So sometimes we call that the effective spring constant. A pendulum doesn't literally physically have a spring attached, but it acts effectively a lot like a spring. And what really matters about the pendulum is what's the mass, but what the new issue is, what is the length of the pendulum? So one example is for a spring, what's the formula for capital T? Here's just one really quick example. What's the spring formula for period? Capital T 2 pi m over k. So what is that probably going to be for a pendulum? Everywhere I see k, I replace it with mg over the length of the pendulum. And the rest of it I'm just going to keep exactly as written. 2 pi square root of mass over all that. Maybe I'll put this in parentheses. Okay. Can you simplify that a little bit? Not too bad, right? If you simplify that a little bit, you'll get the m's will cancel out and the L will end up in the numerator. So guess what you get? You get our standard answer for a pendulum, and our standard answer for a pendulum is 2 pi square root of L over G. And getting from here to here could be one of many, many examples of. Just replace K with mg over length. M ends up canceling out. L ends up becoming very important about this pendulum. Long pendula take a long time to oscillate. If gravity is really strong or gets stronger, it makes the pendulum oscillate in less time. But of course, we can't really very easily adjust the G value here on Earth. We'd have to do something pretty exotic. These two are what most of tomorrow's lab is going to be focused on, maybe especially the one on the right. So I wanted to at least mention it before today's class ended. Okay. Try some of the pendulum formulas, try some of the simple harmonic motion questions in chapter 14, and I'll see you in lab tomorrow with some pendulums. Have a good one. Yeah. Yes, on the lab we can do tomorrow night, sorry.
I was just wondering when you expect
Go ahead.
to get like the test scores and the homework scores and lab scores and stuff out.
I can definitely tell you quite a few of those, the big stuff, the test scores for sure. And I'm pretty far behind on homework, but test scores, I definitely know that. And I know homework scores up through spring break pretty well, or fully. It's the homework since spring break that is behind. I could send you an email telling you your test score, or you could kind of give you a snapshot on kind of where the test scores are at. By test scores, I mean like the 3 tests we've had so far. We are going to have one more. And I think that would be the major thing that I would look at. I can also give you some idea about your homework score at the point I've got it. Most people's homework scores are really strong, yours included, if they've been handing in the assignments consistently, and people have been. So that usually tends to be a pretty strong portion of somebody's grade, like in the 92, 94, 95% kind of range, pretty commonly just estimating. So I could give you an update on your test score. It's written right around here. Where is it? Oh yeah, it's on the laptop.
And I was also wondering about labs because I haven't really gotten any grades from the beginning of the semester, so I don't know where I stand.
Yeah. Sorry about that. Again, people's lab grades are pretty strong as long as they're consistently, doing the labs and handing them in, which is pretty much true for everyone. So, most of the points are for kind of doing the work, and there is grading on how well executed the different parts of the labs are. But again, I'd say that's a pretty strong portion of your grade. And I'm behind on the grading, but I'd say like typically for a typical lab, it's out of 10 points, and kind of 5 of the points are for doing the lab, and then 5 of the points are like kind of me grading the manual, the 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 lab notebook, I should say. Um, and pretty commonly, it's like 3 out of 5, three and I kind of do it in half point steps. So like 3.5 out of 5, 4 out of 5, and 4.5 out of 5 are pretty common. So then you put that together with 5 out of 5 for just having done the lab activity. Um, so a pretty common like lab score is like 8.5 out of 10 to 9.5 out of 10. And I think if somebody does all parts of the lab, they tend to fall in that kind of range on a given week.
Okay.
So again, I know that's kind of general, but I think that's a pretty good snapshot of where you're likely at with lab and where you're likely at with homework if you've been kind of handing in all homeworks and handing in all labs.
Okay. Sounds
Yeah,
good. Thank you.
yeah. And then I'll just say one other thing. Pretty much, you can look at the specific grade breakdown, but I think basically by the end of the semester, homework and lab together, I think make up 45% of the course grade is I think the number, close to 50, but a little less than 50%. And then the 4 semester exams with the final exam overall tests end up being just a little bit over 50%. So something to think about.
Okay. Have a good day.
All right. Bye, Ashley.
Bye.